Last time we gave every token two things: its meaning baked in from the embedding table and its place in the sentence added on as a position signal. So now each token knows what it is and where it sits, but it's still standing alone in the crowd. It hasn't talked to anyone yet. This episode we let them talk. This is self-attention. And honestly, it's the whole reason transformers work. Here's the intuition. Picture the word bank. On its own, it's ambiguous. Money or river? The word can't decide by itself. It has to look around. If river is nearby, it leans one way. If deposit is nearby, it leans the other. Every token in a sentence is doing this constantly, quietly asking, who here is relevant to me? Self-attention is just a clean mathematical way of asking that question and acting on the answer. Heads up, today we build the mechanism on random untrained weights, so it won't actually disambiguate bank yet. That skill only appears after training. For now, we're wiring up the plumbing. So how does a token ask? We give every token 3 different jobs, 3 different projections of itself. The first is the query. That's what am I looking for? Think of it as the token raising its hand and describing what it needs from its neighbors. I'm the word bank, and I'm hunting for context that tells me which kind of bank I am. The second job is the key. What do I offer? Every token also advertises itself. The key is a little label that says, here's what I'm about, in case anyone's searching for something like me. And the third is the value. What will I actually hand over if you pick me? 3 linear layers, no bias, all reading the same input token, each producing a different view of it. Query, key, value. Now the matching. To find out how relevant token A is to token B, we take A's query and B's key and we dot them together. A dot product is high when 2 vectors point the same way. So a big number means your query and my key line up, we are relevant to each other. Do that for every query against every key and you get a full grid of scores. How much each token cares about each other token. Want catch? When head size is big, those dot products are sums of a lot of terms and they can get large. Large enough that the softmax we're about to apply turns razor sharp, putting almost all the weight on a single token. So we scale every score down by 1 over the square root of head size. It's a tiny line of code, head size 0.5, but without it training gets unstable. Small detail, big consequences. Then softmax, we take each row of scores and squash it so the numbers are all positive and sum to exactly 1. Now each row is a set of attention weights, a spotlight. A trained model might put 30% of its attention on one neighbor and a sliver on the rest. Our untrained head spreads its attention almost evenly. That's expected. The shape of the operation is what matters today. The sharp, meaningful spotlights come once we train. And the payoff, the output. For each token, we take those weights and use them to blend the values of every token. High weight, more of that token's value flows in. Low weight, barely any. So each token's new vector is a custom mixed cocktail of the whole sentence, weighted by relevance. Once trained, bank would literally pull in a bit of river and become a more contextual version of itself. That's the magic, that's attention. But hold on. Look closely at what we just built. Token 4 was allowed to peek at tokens that come after it, tokens 5, 6, 7. For a model whose whole job is predicting the next word, that's cheating. It's reading the answer before guessing. We have to forbid it. That's next episode. Bezo overview. Okay, code. This file is short, about 3 dozen lines, but every line earns its place. We import torch, set a seed, define a head module, instantiate one head, run a fake batch through it and print the evidence. It splits cleanly across 2 screen pages, the module on page 1, the run and print on page 2. Let's walk it top to bottom. Up top, the imports and the setup, torch, torch.nn and torch.nn. functional as f. We fix the seed with torch.manual seed, so the random numbers and therefore the exact attention weights you will see in the terminal come out the same every run. Then 3 numbers that define our toy problem, batch of 4 sequences, 8 tokens each, 32 channels per token. We call them BTC. That 4832 is the shape flowing in. Here's the head itself, a small nn.Module. In init we create the 3 projections, key, query and value, each an nn linear that maps from C, 32, down to head size, which we'll set to 16. And notice biased or false. We don't want a learned offset here. These are pure linear maps, just rotations and rescalings of the token vector. 3 layers, same input size, same output size, 3 different sets of weights. The forward pass, the heart of the file. We push the input x through each projection to get k, q and v. All shape, b, t, head size. Then the scores, q at k transpose 2, 2, 1. We transpose the last 2 dims of the keys, so the matrix multiply lines up every query against every key, giving us a BTT grid, 8 by 8, 1 score per token pair. And right there on the same line, we multiply by k dot shape, 0.5, that's head size, 0.5, the scaling we talked about, read straight off the key tensor. Then f softmax along the last dimension, dimmed sobered 1, which normalizes each row to sum to 1, our attention weights. And the final line, weights at V matrix multiply the weights by the values, and out comes B, T head size, 4, 8, 16, each token's new context blended vector. We return both the output and the weights so we can inspect them. Page 2, we actually run it, make a random input x of shape for 832, build a head with head size 16, and call it inside a torch. No grad block, so the printout stays clean. Then we print the attention weights for 1 row, token 4 in the first sequence, so you can see them sum to 1. We print the output shape, and we print a tiny human readable read of where token 4 spent its attention. Notice the weights are all close to 1/8. That's an untrained head. It hasn't learned to prefer anyone yet. The 2 it leans on most happen to be tokens 4 and 7. B6 closer, teaser. And there it is, one attention head from raw tokens to a blended context-aware output in about 3 dozen lines. But remember that problem we spotted? Token 4 was allowed to look at tokens 5, 6 and 7, the future. Next episode, we add one triangular mask that slams the door on every future token. Causal masking, no peeking. That single trick is what turns this into a real language model.